Good morning, everyone. Happy Friday. Welcome to TVE Happy Math Hour, our weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come back and watch it. This session will provide Tejano Passport points, and the code will be posted on the chat towards the end of the session. So now, at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Without further ado, I'll pass it on to our presenter so that we may begin.
Good morning, everyone. And again, thank you for joining us for another Friday Happy Math Hour. Again, all of you who are here for Math 1314, you will stay with me. Anyone who's here for Math 1324, you will find the link to the 1324 session on your chat. So again, let's go ahead and get started. So for today's Friday Happy Math Hour session, we are doing exponential and logarithmic functions. All right, so let's start with what an exponential function is. So this is the book definition of an exponential function. An exponential function is something that has exponent, of course, and to this exponent we have the a, which is called our base. Okay, the domain for all exponential functions is all real numbers. Okay, this will never change. The domain for an exponential function will always be this. It's a set of all real numbers. Although the range is going to change according to all of the positive numbers that are given by the function itself. So the range is a set of all positive real numbers. So this information will change. Okay, the range will vary depending on the function, but for the domain, it will always remain constant. It will always be all real numbers. Okay, now I like to start exponential functions with giving my students a riddle. Okay, and the reason why I start with a riddle is because exponential functions can be a little bit tricky and a little bit dangerous. And what I mean by that is they grow really fast. So here's my riddle here. So suppose that you receive a penny on the first day of class, and then 2 pennies on the second day of class, 4 pennies on the third day, 8 pennies on the fourth day, and so on and so forth. And we would continue this until the 31st day of school. Okay. Um, would you like to take this option of getting 2 pennies and being doubling for 31 days? Or would you rather take a lump sum amount of $1 million? Okay. So, I asked them which one you would want to take. And again, most of my students would say that they want to do the $1 million. But this explanation that I'm talking about, if we try to do the solution here with the pennies, okay, if I want to complete this table, okay, day one, day two, day three, okay, and according to the days, it's the number of pennies, okay, I would have these, as you can see, exponential values. My base would be 2, and my exponents would be the days coming up. So if I would continue to do this for um, 31 days, okay, what I would have to do is I would have to evaluate using my calculator my base 2 to the 30th power. Okay, so when I do that, what is this value? What is 2 to the 30th power? And if I put it on my calculator, okay, I would see that I get these 1 billion or trillion pennies. But again, we're talking about pennies. Let's convert that into dollars. So we need to move the decimal place 2 decimal places to the left. Okay. So if you decided to take the penny option, you end up with 10 million, over 10 million instead of just 1 million. Okay. So the reason why I give this riddle is to show you that when working with these problems, with exponential problems, you got to be careful with your rounding. You can't change a penny on these problems. You can't round until you get towards the end, because if you change a penny, your answer is going to be off by a lot. Okay, exponential functions grow really fast. Okay, so just keep that in mind. All right, so let's go ahead and start with some of the material. Okay, um, this explanation that I gave to you is this representation, and I did it for two reasons. One, to show you how exponential functions can grow really, really fast, but at the same time, this function here is my parent function of all exponential functions. Okay, so f of x equals to 2 to the x is a model that we'll be using a lot in this section. Okay. So let me give you the graph of my parent or general exponential function, okay? An exponential function is, again, a function that has an exponent to a base, okay? The graph of this is all positive real numbers, okay? So my domain in integral notation is from negative infinity to positive infinity. Now my range here is, again, just the positive values from 0 to positive infinity, okay? The exponential function here is going to have a y-intercept at 1, okay? And if I'm reading my graph, again, we read graphs from left to right, my graph is increasing. It's constantly increasing from left to right, okay? Now, all exponential functions have what's called a horizontal asymptote. And we've covered asymptotes already in this class. And again, an asymptote is an imaginary line that the graph does not cross or touch. It gets very, very close to this horizontal line at y equals 0, but it never crosses it or touches it. Again, and for it to be a function, it has to be continuous, right? There can't be any breaks, sharp turns, or curves, right? Okay, so let's look at some other examples of exponential functions, okay? And I always like to introduce this one, 2 to the negative x, okay? So when we're doing math, we know that there's no such thing as 2 to the negative 2, okay? We can't evaluate that. So we use our properties of exponents. So we apply the negative exponent rule to be able to solve for this exponent. So 2 to the negative x is the same thing as 1 over 2 to the x, and I can also put it as a power rule that 2 to the negative x is equal to 1 half to the x power, okay? And I like to throw this one out there because in your homework, you're going to see all these variations of this type of um, exponential function, but they all produce the same graph. Okay, so if I break down the graph, again, my graph for this function um, is all the values that are between 0 and 1. Okay, my range is all positive real numbers from 0 to infinity. It continues to have a y-intercept at 1. Now, but this one is decreasing, right? It's going the opposite direction. My parent function was increasing. Now, since my x is negative, I have a reflection on the y-axis. It's decreasing. Okay, it still has a horizontal axis, a horizontal asymptote at y equals 0. And again, this graph is continuous. Okay. All right, so if I wanted to graph other exponential functions with different bases, okay, the way I like to tell my students is think about this. If 2 pennies in 31 days gave you over $10 million, what if I gave you 3 pennies and I started doubling that? Well, of course, your amount would be a lot bigger, right? So again, if I change the base of an exponential function, what that's going to be, it's going to make my graph grow a lot faster. Okay, so let's look at the graph of this. Okay, so to practice also evaluating our exponential functions, let's put in values. Okay, so I want to evaluate for x equals -2, x equals -1, x equals 0, and x equals 1. Okay, so when I said x equals to -2, I get a y value of 1 over 9. When x is equal to -1, I get a y value of 1 over third. But here, this is my y-intercept. How do we find the y-intercept? We set x equal to 0, and we have our 0 property for exponents. Anything to the 0 power, your answer will always be 1. That's why my graph always has a y-intercept at 1. Okay, so 3 to the 0 is 1. So keep this value in mind. And then we have our identity, right? 3 to the 1 is just going to give us 3. So if I plot these points, again, I plotted these points. I'm gonna do a smooth curve and I'll let the system draw it for me. Okay. I have this continuous curve that is increasing. Again, if I were to match it with my parent function with which was for fx equals 2 to the x, it would be a large, wider curve. But because my base is 3, it shoots up really, really fast. Okay. All right. So what we want to do is we want to determine if a function is a function, right? So for us to determine if a function was a function, we would do our vertical line test, right? So um, we are going to study also if it has an inverse. So to find an inverse, we do the horizontal line test, right? So I think we've covered this already. So to determine if it's a function, we use the vertical line test. To determine if the function is one-to-one or it has an inverse, we would perform our horizontal line test. Okay. So for our problem, okay, it passes the horizontal line test. My imaginary horizontal line will only cross my graph only once. Okay, so that means that my graph has an inverse. Okay, so the one-to-one property says that um, for two exponential functions to be equal to each other, they have to have the same base and they have to have the same exponent. Okay, this would make sense, right? So, for instance, um, if I had this problem here to solve, 10 to the 2 minus 4x is equal to 10 to the 6x minus 1, okay? Um, these two exponential functions have the same base. So for them to be equal to each other, their exponents have to also be the same. So the question is, can I use my one-to-one property for this problem? The answer would be yes. And to solve for x, what I would have to do is just set the exponents equal to each other and solve for x. Okay, so give me 1 second. Okay, so then my exponents are 2 minus 4x equals 6x minus 1. Okay, and I'm going to solve for x. So I like to have the variable on the left and all the numbers on the right. So to do that, again, I'm going to subtract 6x on both sides. I'm going to subtract minus 2 on both sides. And I get this. Negative 10x is equal to negative 3. So to solve for x, I'm going to divide both sides by a negative 10. And when I do that, I get x is equal to 3 over 10. So again, when solving exponential equations, I can use this powerful property that's called my one-to-one property. Okay, so let's see. Can I use my one-to-one property for a problem like this? We have 4x plus 1 is equal to 64. Well, we don't see an exponent there, but the answer would be yes, right? We can possibly use our one-to-one property if we can convert the 64 to be an exponential number, right? So um, what I can see is I can rewrite this equation so that both sides have the same base. Okay, so if you don't see it, okay, you can do a factor tree and divide this number by 4 because that's the one at the base that I want, and you're gonna find out that 64 is divisible by 4 3 times, right? So like again, we could do one at a time. 4 will go into 6 one time, remainder 2. 4 will go into 24, remainder 6 and excuse me 4, and then we can divide again, right? So we have this exponential function. 4 is equal to x plus 1 is equal to 4 to the third. So now it's clearly we can see that we can use our one-to-one property. So my one-to-one property states that for two exponential functions that have the same base, the exponents have to be equal to. So then what I'll do is I'll set the exponents equal to each other, apply my one-to-one property. So my exponents are x plus 1 is equal to 3. And then I have to solve for x. So to solve for x, I'm going to subtract 1 on both sides. And um, um, I am going to get 3 again. So I don't have the subtraction here. So subtract 1 on both sides. So 4 minus 3 minus 1 is 2. Okay. All right. So let's look at this other example. Um, and the answer is there, right? We can use our one-to-one property as well for this one. The first thing that I would need to do is I have a number, the 125. Can I make that into have a base of 5? The answer is yes. 5 to the third power will give me 125, but it's as a denominator. So I can use my negative exponent rule to make that become a numerator value, right? So what you do is you take the reciprocal of this fraction, and by me taking the reciprocal, you change the sign of the exponent. In the bottom, it was just 5 cubed, but by taking the reciprocal, it becomes 5 to the negative 3. Now we see that we can apply our one-to-one property that says that for these two exponential functions to be equal to each other, the exponents have to be equal. So I set my exponents equal to each other. So x minus 3 is equal to negative 3. Add 3 on both sides, and I'm going to find out that x is equal to 0. So for these two exponential functions to be equal to each other, x has to be equal to 0. And then we can verify our work. I didn't do that before, but again, we can always verify. Plug in 0 back into the left side. So we had 5 to the 0 minus 3 power. So 0 minus 3 is negative 3. Take my negative exponent rule because I can't evaluate that. So that's going to give me 1 over 5 to the third power. And 5 to the third power is 125. And we have a true statement. Okay. All right. So most of the examples that we did right now all had to do with a science base, the ones that we use for math and science. Okay, but we also have what's called our natural base. Okay, so our natural base is this symbol E for our base. Okay, E is a symbol. Just most of you are familiar with the pi symbol. Pi represents 3.14. Well, this base E or the symbol E is also a symbol that represents an irrational number, and that's a number that never repeats, never ends. And E is, with just a few decimals, is 2.7182, and again, it goes on forever. Okay, so we call this the natural base. Okay, e to the x. Okay, so let's review this. E to the x. So believe it or not, this e to the x is going to have the same graph that my parent function was for 2 to the x, okay? It produces a continuous graph that is increasing. It has a y-intercept at 1. It has a horizontal asymptote at y equals 0, okay? So um, most of the times we will use this, we like to use these for our business, okay? All right, so we can apply the same rules to my natural base. And if we see here, we can use our one-to-one property to solve these as well because they have the same base. I have a base e to the left, I have a base e to the right. So my one-to-one property says that for these two exponential functions to be equal to each other, my exponents have to be equal to each other. So that's what I'll do to solve. I'm going to set the exponents equal to each other. So we have x squared minus 3 is equal to 2 to the 2x, excuse me. And I see that I have a quadratic. And I have a quadratic because I have an exponent to the second degree, right? So what I'm going to do is I'm going to move everything to one side. So since there's only one term on the right, I'm going to move that one to the left, okay? So when I do that, okay, I'm going to have this. X squared minus 2x minus 3 is equal to 0. And now you see that we have a quadratic that we've been working with all of chapter 1 and chapter 2. So there's several ways that we can solve this. We can factor, we can use our quadratic formula. So in this particular problem, I'm just going to factor. That's the easiest, most straightforward to solve most of them if they are factorable. So I know that x squared minus 2x minus 3 factors into x minus 3 times x plus 1. So I can use my zero rule to solve for x. And my zero rule says that when I am multiplying two numbers, the only way that my product can be equal to zero is if one of these two are zero, right? So again, if we don't see it, we will have these two options, whether x minus 3 is equal to zero or x plus 1 is equal to zero. And hopefully we can see now that the two solutions for this is x equals 3 and x equals negative 1. Okay. All right. So now let's look at a exponential function or equation in a real world scenario. Okay. So um, a, a great example of this is what we have in front of us. It's called the compound interest formula. Okay, so they chose A. If you're wondering why they're using A, in the real world, this is called the annuity formula. So A for annuity, but for us, the way we want to learn what these variables represent is by using these definitions. I want you to think of A as our future value of an investment. P is called our principal, but I like to call this our future value. Okay, so if you want to purchase, let's say, a car now or a home, um, we have what's called our present value, but after taxes and all of that, we'll have a future value. Okay, R is referred to our interest rate. Now, just like when you go shopping, every time that they give you a discount or a rate, it's always in a percentage. But since we're going to apply these percentages into a formula, make sure that the rate is represented as a decimal. Okay. And then let me skip over to the t. T in our equation here represents time, t for time, okay? And that's always the number of years, okay, that we're going to be calculating. So the term that can be a little tricky, or the variable that's going to be tricky here, is my n. N represents the number of compounding periods. Now there's several representations for n. So here they are. If you have a word problem and the problem says that the interest is being taken semi-annually, that means that it's twice a year. So your n would equal 2. If the problem says the interest is taken quarterly, okay, the way I like to tell my students to remember this one is how many quarters are there in a dollar? Well, that's 4. So when you see quarterly, your n will be 4. Like on the monthly, how many months are there in a year? Oh, there's 12, so n would be 12. And if the problem says that the interest is taken daily, well, there's 365 days in a year, so your n will be 365. Okay, so these are the values that n can represent. So let's go ahead and look at a problem. Find the amount to which $1,500 will grow if deposited in a bank at 5.75% interest compounded quarterly for 5 years. Okay, so here they're giving me the present value, the 1,500. They're giving me the R, 5.75%. They're giving me the N, which is 4, and they're giving me the time, which is 5. So let's just plug it in. Okay, so this is what they're giving me. And let's plug it into my compound interest formula or equation. And once I plug all my values in, you have to be careful with these exponential functions. You want to do all of the operations and not round until the end. Now, also, you see the answer, it's right here already, but there's several things also that I want to caution my students, okay? This problem didn't tell me to round, right? So, but what are we dealing with? We're dealing with money. So sometimes your homework is not going to tell you to round accordingly. So you got to make sure that you round to only two decimal places, because the two decimal places means the cents, right? So again, when I plug this in, we have to follow order of operations. We got to do everything that's inside my parentheses first. So I would do the 0.0575 divided by 4, because you do multiplication and division first before you do addition, right? So when I divide these two numbers, I'm going to get an answer. I'm going to add it to 1, and then I do the exponents. 4 times 5 is 20. Take that value to the 20th power. And then the last thing I'm going to do is I'm going to get that value multiplied times 1,500. And that's going to give me this answer, the $1,995.55. Yes? So um, let's look at another real world problem. So a couple just had a baby. How much should they invest now at 5.8% compounded daily in order to have $35,000 for the child's education in 18 years from now, right? So hopefully, um, some of our parents would do this, right? They want to save for our education. So once we were born, they start saving up for that college because college is expensive, right? So let's see, how much would we save if we did this, if we set up a fund, right? So what we're trying to find out is our present value. How much should we invest now in order for me to make sure that I have $35,000 for my child to attend college, right? So we're going to use our compound interest formula. We have our future value, which is the 35,000. We have a rate that I converted into decimal. Oh, there's a typo here. This should be 0.058, not 75. I think we fixed it later. Again, it said that we want to compound it daily. So that means every day. So my n is going to be 365. And we're going to do it for 18 years. So t is 18. So let's go ahead and plug it in. Let me see if I plugged it in correctly. Yes. So now this is correct. So this is my correct rate, the 0.058. Again, I'm going to follow the order of operations. Divide this number by 365. Add to 1. Um, take this power to the 365 times 18. Let me see. I think I did some of this work. Yes. Okay. I did my work to show you. I do not want to round. I'm putting everything that my calculator is giving me. Okay. Do not take off any of these values from your calculator because, again, take off a penny, your answer will be wrong because it'll be off by a lot. Okay. So I add this number, I am going to get 1.000158904. Again, 365 times 18 gives me this value, 6,570. Okay, I'm going to take this value to that exponent value, and that gives me 2.840320963. So to solve for my present value P, I'm going to divide both sides by this value. So P is equal to the 35,000 over the 2.840320963. And that tells me that, again, in order for me to be able to have $35,000 in 18 years, that my financial institution, and that's how they work, okay? When you're trying to save money, the interest is very low. But if you have a credit card that they're collecting money from you, this interest is very high, okay? But you see here for us, uh, for me to have this amount, I need to deposit $12,000 um, um, to invest my present value and to get the total of 35,000. Okay. All right. So again, for application purposes, okay, when we're dealing with compound interest formula, we're going to have two formulas. I did examples of this first one, okay, which is just with our compound term. But we have another formula that is called our continuous compound interest. And the continuous is very similar to my 365 when for n, but it's slightly different. Again, we're using our natural base, okay, the base E to solve for problems. So let's see. Oh, I don't have an example. So let's go ahead and apologize. I'm going to move on. This was section 3.1 in our homework. Let's move to 3.2. Okay. So 3.2 is the inverse of my exponential function. So it's the opposite of exponential functions. Okay. So um, log functions have a lot of similarities to my exponential functions, but again, because they're opposites of each other. So let me show you them back to back. Okay, this is my parent exponential function. Y is equal to 2 to the x. Okay, it's a increasing function. It has a y-intercept at y equals 1. It has a horizontal asymptote at y equals 0. And if I were to plot my inverse function, which is my logarithmic function, my logarithmic function has an x-intercept at 1. It has a vertical asymptote at x equals 0. Okay, it's increasing as I go up. It's increasing as I go up. It's continuous. There's no breaks. Okay, and if you see here, my axis of symmetry is my y equals x line. Right. This is creates the mirror image of my exponential function and my log function. Now let's review here. What was the domain of our exponential function? Well, the domain of my exponential function was all real numbers from negative infinity to positive infinity. And my range was all positive values from 0 to positive infinity. Well, guess what? It's opposite to my log function. The domain of my log is going to be what the range was for my exponential function. So the domain for my log is from all positive real numbers from 0 to positive infinity, and my range is going to be all real numbers. It's from negative infinity to positive infinity. They're completely opposites of each other. Okay, so let's go ahead and look at also our natural logs. Okay, so the common log for the sides is base 10. Why base 10? Because we have 10 digits to count. Okay, so in your homework, if you don't see a base down here, okay, we are automatically assume it's a base 10. Okay, so we also have a natural log, just the way we had a natural exponent, we have a natural log, and we call this the ln, natural log. Okay, so the natural log is the same thing as log to the e to the x. Again, e is a symbol that represents a number. Okay, so um, let's do this. Most students did dislike logs when they were probably in high school because your calculator couldn't solve all logs. Your calculator can only solve logs of base 10 because those are counting numbers. So um, what we can do, since logs are inverses of exponential functions and our calculator can calculate any exponential value, we can do that. We can convert a log function to an exponential function, and we were going to do it this way. Okay, um, logs also have a base like an exponential function. Okay, so if I wanted to convert this log into its equivalent exponential form, okay, I start with the base. So um, oops, I clicked one too many. So the way I would do it is here. The base of my log is 4, so that would be the base of my exponential. Okay, since 16 is the input to the log, the 16 is going to be the output of my exponential. And
You lost connection. He's coming back in the room. Have no worries.
I'm back. Sorry, guys. Can you all hear me?
Yes, sir.
Okay. Do apologize for that. Um, all right. Let me continue again. So here, um, the output of the log is my input of my exponential function. And if I see here, um, 4 to the x is equal to 60. Now what I can do is one of the things that I had done before, I can use my one-to-one property, right? I can convert the 16 into a base 4, and I know 4 times 4 is 16, so this would be 4 squared. So what would be the value of x? The value of x would be 2. Okay, so again, this is one way that we can solve logs and by converting them to our exponential equivalent. Okay, so now that I did this first one, x is equal to 2, let's go ahead and try this next one. Um, um, we can also work backwards. Since I have the answer here, I want to show you that I can also work backwards. And you might have a test question that might ask you this. Convert the log into its equivalent exponential form. Or they might tell you, take it, given this exponential equation, convert it to its equivalent log form. Okay, so if I want to do that, again, the base of this exponential is 5, so that's going to be the base of my log as well. So here, I would do log for log. It's a base 5. Okay, the input of the exponential is the output of the log, so to the third power be equal to what the log is. The output of the exponential is 125, so that's going to be the input of the log. Okay, and this is how I can convert from exponent to log. Yes. So let's just do one more example again, and I like to review always the logs because that's the one that's going to be the most useful for us. So again, on this one, they didn't give me the base; it's just the base b, but I can do this. Okay, so the base b of this, the log of this base is base b. Okay, so let me convert it. So the base of my exponent is going to be b. The output of the log becomes the input of the exponential, and the input of the log is the output of the exponential. Okay. Um, can you all put the link to the 1324 again on the chat? Ah, thank you. All right. Um, so let's try one more. Okay. This one I like also because it's giving us another symbol. So we have the radical symbol. We have the square root of 81 is equal to 9. And what we want to do is we want to convert this equation into its log form, but we don't see an exponent, but we do. The square root is a symbol that is represented as an exponent. The square root is the same thing as a 1/2 power to the number. So 81 to the 1/2 power is the same thing as the square root of 81. So now I see that I do have an exponential. So the base of this exponential is 81. That's going to be the base of my log. So my log is going to be a base of 81. The input of the exponential is the output of the log, so that's going to be equal to 1/2. The output of the exponential is the input of the log. So this is log of 81 to the 9th power. Okay. All right, so let's review some properties. Okay, so the first one here is um, my identity property, which is, and they're back to back. I can show you the log and the uh, the exponential. So, excuse me. So the first one here, if I have a log, it doesn't matter what the base is. If my input is 1, the answer will always be 0. Okay? Just like when I was talking about my exponential. Anything to the 0 power on the exponent, the answer is always going to be 1. Now it's backwards. If I input 1, my answer will always be 0. Okay, this one's my identity property. When I have a log of base A and my input is A, I'm always going to get 1 as the exponential. A to the 1 is just A. Yes? Okay. So this third one is an inverse property that these are very similar, like taking the square root and squaring it. The exponents become 1. You all like to say that they cancel, but they just give us back the input, just the input x. Okay. So, and then the last one is the one-to-one property, just like what we saw for exponentials. Therefore, two logs to be equal to each other, they have to have the same base and they have to have the same input. So let's go ahead and do some of these. Okay, let's use properties to solve. Let's not use a calculator. So what I'm going to do first is that 127, can I make that have a base of 3? So the answer would be yes, right? So 27 um, can have by converting this, well, I see that we're going to solve this a different way. So what we're going to do to solve this one, instead of using our properties, let's convert it to our exponential form. Okay, so let's do that. Let's convert to our exponential form. So the base of this log is 3. Okay, so that's going to be the base of my exponent. Um, the output is the question mark, what I'm trying to solve for. And then my input of the log is the output of my exponential. But then again, this is where I was going to start. This is how I would start. I would convert the 127 into an exponential equivalent. Okay. And I would see that I can rewrite 127 that has a base of 3. And I know that I can do 3 to the third power. 3 to the third power is going to give me 27. But again, I'm going to apply the negative exponent rule, take the reciprocal, change the sign of the exponent, and I have this, 3 to the negative 3. So for this to be a true statement, what does my question symbol have to be? Well, that has to be negative 3. Yes, so that's my answer. And what I used was my last one, my one-to-one property. Yes? And again, there's several ways of solving this. There's not just one way. We have 4 rules. We can use any of those rules to solve these problems. Okay? Just keep that in mind. All right, so again, these are my properties. And the properties that I used again was my one-to-one property. Okay. Um, but like I said, which do these properties resemble? If I were to put them all together, okay, we see that we can represent my inverse property, or like I said, we use the one property to solve. So there's several ways to solve these problems. Okay. So let's go ahead and um, do another example, okay? Use properties to solve this log. Log of pi to the fifth, okay? Um, which property does this example resemble, okay? So I don't know about you, but what I can see is, again, this is my inverse property, that I have something of a base a to the exponent, which is what I have here. I have a base of pi, then I'm inputting pi. So what's going to be my answer in my inverse property? The answer is x, but x in my example here is 5, right? So that's what's going to be my answer, 5. Yes? You going home? This one should be easy, right? I have a log and it's 7.5, but my input is 1. Which property does this resemble? My first one, right? That says that I don't care what the base is. If I'm inputting 1 to this, the answer will always be 0. Yes? Okay. All right. What about this one? Log of 90, log of base 90 to the input 90. Okay. And this one again is our second property. The identity that if I have a base to the same input, the answer will always be 1. Okay. All right. So again, it's very useful to memorize and know these properties. Okay. All right. So what about this last one? 3 to the log of base 3 to the 8. Okay. So this one again looks like it's my inverse property. It's this the first one. The second one here, that I have a base exponent of 3 taken to an exponent of log of base 3. So the input's just going to be x, or in this case, it's the value of 8. Yes. All right. So um, solving for logarithmic functions, there's several ways we can solve. And one of them is, again, using our properties, or we can also do our conversions. Okay. So on this particular problem, okay, what I'm going to do to solve is I'm just going to convert it into its exponential form. The base of this log is base b. So it's my exponent is b. My input is 1000. It's the output of the exponential. The output of the exponential is the output of the log is the input of the exponential. So what would be the value for b that gives this a true statement? And I can see that I can convert the 100 into a exponential part. 100 can be written as 10 to the third power. So here I'm using my one-to-one property. The exponents are the same, but for the equation to be a true statement, the bases also have to be the same. So then the base for this problem has to be 10 in order for it to give me a true statement. Okay. All right, what about this one? The log of base 6 of input x is equal to 5. Okay, what I can do is, again, let me go ahead and convert it into an exponential form. The base of this log is base 6, so the base of my exponential is 6. The input of the log is the output of the exponential, and the output of the log is the input of the exponential. This one is a calculator problem. To solve for x, I just have to put into my calculator 6 to the 5th power, and it's going to give me the answer, right? Which is going to be 7,776, okay? Unless someone knew it. All right. Um, Again, most of these that I solved was just converting, but again, I could have used other methods to solve these problems. Okay, you have four other properties that you can use. Okay. All right, so again, um, to elaborate on some of our log properties, we have some additional properties that we need to know. Okay, um, so let's start with number 5. These 1 through 4 we already covered, but these are some new ones. 5, 6, 7, and 8 are new. So the first one is called my product rule or product property that says that when I have a log of a base and in that base I have two values that are being multiplied by each other, I can expand this log into two logs. This is the same thing as the log of base b of m plus the log of base b of n. And something similar to this is if you know your exponential rules. For instance, if you have x squared times x cubed, how do you get the solution? Well, you add the exponents, right? You get x to the fifth. The logs have the same product property. Okay. Opposite of multiplication is division. If I have a log of base b and I have two values that are being divided by each other, I can expand this log by subtracting the logs of the same base. So it would be the log of base b of m minus the log of base b of n. Okay. Number 7 is called the power property or power rule that says that when you have a log of base b to a value and you have an exponent to that value, you can multiply that value to the log. So here would be my exponent is p. I would multiply p to the log of base b of m. Okay. And then the last one is the one that we've been covering, which is our one-to-one property. That for two logs to be equal to each other, again, we covered it already, and the bases have to be the same, and my inputs have to be the same. Okay? All right, so let's go ahead and solve this logarithmic equation. We have the log of base 5 of x plus 1 is equal to the log of base 5 to the ninth. Oh, so I can use my one-to-one property. Since I have two logs that are equal to each other that have the same base, the inputs have to be equal to each other. So that's what I'll do is, again, I'm applying my one-to-one property, which is the last one, and I'm going to set the inputs equal to each other. So we have x plus 1 is equal to 9, solve for x, subtract 1 on both sides, and I'm going to get x is equal to 8. Okay. Um, and we always want to double check our work. Replace the x with 8, and I see that 8 plus 1 is 9, and we have a true statement. The log of base 5 of 9 is equal to the log of base 5 of 9. Okay. Always double check your work. All right. How about this one? What property could we use? Um, so the first thing we would ask ourselves, well, what's the base of the log on the left and what's the base on the log on the right? So again, since they didn't write down a base, you don't see a number there for the base, we automatically know that this is a base 10. That's the default. Okay, if you don't see a base, it's base 10. So we can use our one-to-one property because we have a log that has a base 10 on the left equal to another log of base 10. So to these two logs to be equal to each other, the inputs have to be equal to each other. So that's what I'll do to solve. I'm going to put 17 is equal to x squared plus 8. I see that I have a quadratic, so I'm going to subtract 17 on both sides. Um, 8 minus 17 is going to give me x squared minus 9. So on this one, again, I know that this is a perfect square. So I can use my difference of squares, or I can use my square root property, could use my quadratic. But again, we want to um, um, choose the easiest one, or the ones that's most common to us. Again, on this example, I'm just going to use my square root property. Means I'm going to solve for x. I'm going to add 9 on both sides, take the square root of both sides, and I'm going to find out that x is equal to the square root of 9, and the square root of 9 is plus or minus 3. And we always want to check our solution. Okay, we would plug in a positive 3. Positive 3 squared is 9. 9 plus 8 is 17. Okay, the positive works, but the negative one also works because it's a square. Negative 3 squared is going to give me a positive 9 again. 9 plus 8 is going to be the 17. Okay, so always double check your work. Okay, so these two are both solutions. What about this one? Which property can we use for this one? So here, again, we're using the natural log. They're the same, natural log on the left, natural log on the right, so I can use my one-to-one property, yes? Okay, so I can use my one-to-one property, so I'm gonna put my inputs equal to each other. Um, so we have x squared minus 3x is equal to 18. Again, I have another quadratic again. Um, so I'm gonna subtract 18 on both sides. So we have x squared minus 3x minus 18. Again, there's several things that we have under our arsenal to solve for this. Okay. Again, what I'm going to do is I'm going to factor this quadratic out. And I have x minus 6 is equal to x plus 3. Again, I'm going to use my zero property to, or rule, to solve for x. The only way that I can get a product of 0 is either x minus 6 is equal to 0, or x plus 3 is equal to 0. So I have two solutions, x equals 6 and x equals negative 3. But we cannot forget to double check our work. So let's plug them in. Let's see if they work, okay? So, um, so again, if I check them in, I'm going to see that both of them work and I'm okay, yes? So let's do the last example here. Um, we have the log of base 4 of x plus 6 plus the log of base 4 of x minus 6 is equal to 3. Um, which property would we need to use first in order to solve? So this one's going to be, we're going to have to use multiple properties to solve for this one. And if you see here, what we want to do is we want to add these terms. And again, we're gonna deal with most of these sections in 3.3. So I won't solve it because we haven't covered it yet, but we will get to it. Okay, so this does conclude my session for today. I thank you for all for joining us. If you joined in late, or if I went too fast, again, you can download my presentation. Just click on the little box with the arrow on the top, and you can download this. If not, you will find this uploaded to our YouTube channel later on. Again, thank you so much and have a great weekend. I'll pass it back to our presenters.
Thank you, Mr. Carrizales, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on the YouTube playlist. Today's session will also be available on the playlist later on today. Also, link to the short survey to help us improve our TVE sessions. Please take time to fill out the survey. Before you leave, I want to share the TVE sessions that we will have next. We'll be back next week with a Happy Math Hour, which 1314 will be covering the properties of logarithms and exponential logarithmic equations. And Math 1324 will be covering basic matrix operations and inverses. And for next week's student success topics, we'll be covering the dog fostering with Miss Olivas. So today at 1 p.m., you could also join us with a student success topic, which will be EPCC libraries, which will be presented by Blake Kamazara. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or mic. Have a great weekend, guys.